All right, we're back with part 2 of this. So we'll do the second problem. Easy enough. Now notice right away, the setup really hasn't been changed. All we've got is a signal source here. Whoops. I'm going to turn the camera down so you can actually see the equipment. The signal source here coming in to the yellow wires. That's these two red ones. I should have chosen one with red wires, but anyway, there we are. And now we can measure the output. Now notice these values here are the same as up here in your first part. I've changed nothing. I'm still at 100 hertz. So you can cross this out. It's not kilohertz. It's just 100 hertz. And we're going to remeasure and measure these values here. You can change the peak value, but we want the maximum. So we're leaving it at 2 volts. Our picture is still good here. So I'm going to measure again. We'll check 1 and 2. Well, I'm set up. I've got 1 and 3. So this is 0.8 right here. It's 0.8 volts. And if I go back now to the center, and notice things are in phase. The last time we measured them, they were out of phase. So now we've got 0.4 volts. And you know, if you want to check this, we could even make this plus and minus 1 volt. And notice how we just get a tighter value for 0.4. I don't know what else is down there if you really want to, 500 millivolts. See, they really kind of lie right underneath each other. So it's peaking out here at plus 400 millivolts. I'm going to back it down one. So they are very much in phase when I hook the wires this way. But remember, I can reverse them and they'll be out of phase. One of the things about the transformer that we haven't, we talked about in the lecture is it is able to isolate between the input and the output. You notice the connection here between V1 and any of these outputs. There's no electrical wired connection. This is a magnetic connection. So down here, I can connect up the hard ground, which connects to all these metal parts. I can connect that to one side, and then I can connect the other hard ground to either side that I want, because the transformer isolates those two grounds out here at the signal level. And we'll take advantage of that next week when we make AC to DC power supplies. Okay, so let's see. So we have these measurements. This one is 0.4. This one is 0.8. The frequency is still 100 hertz. So now it wants to know, what is the turns ratio between the secondary pins 1, 3, and the primary? Okay, so you're going to want to do the secondary pins 1, 3, and the primary. I'm going to pause a second and see if I can get a pen into this action. Okay, so I'm having no luck being able to bring a pen in. I can do it if I'm doing a slideshow, but not individually here. So here's one thing I can do. What did we have? Back in the previous, maybe I can just type in some numbers here. For V12, I'll bring this up. We had what? 0.4 volts peak. And for V13, we had 0.8 volts peak. The frequency was still 100 hertz. Okay, so now it says, what is the turns ratio between the secondary pins 1, 3 and the primary? What is the turns ratio? Remember, this primary peak up here was 2. So what's the ratio here? Remember the deal, the ratio is equal to the voltages on the output to input. So we can say the ratio between secondary pins 1, 3. So we want voltage of the secondary, I'll make it a small s, divided by voltage of the primary, right, is equal to, got to erase a bunch of this stuff, is equal to what? The voltage of the secondary is 0.8 divided by 2. All right, we can use our trusty calculator and get that, and that looks like it's 0.4. That looks like it's 0.4. So that would be the turns ratio, right? So that's a voltage ratio. How do you express that as a turns ratio? 4 to 10. We'll get this all to sit on one line, okay? Now you can do the same thing with this question over here. The turns ratio between the other pins, secondary pins 1 and 2, that's 0.4 divided by 2. So that's going to be, what, an even smaller number. All right? Now, what else is going on here? We have this all set up. It's pretty easy. You're going to make this graph. And I didn't hand draw one this time like I did before, but I have it right here. This is the graph we're making. In the circuit above, use pin 2 as the oscilloscope ground. Okay, let's switch that around. So now it says, use pin 2 as the oscilloscope ground. That means connect the black one there. And then use 2 channels to display pins 1 and 3. All right, so there's going to be the one for channel. I got to be careful that I take off. All right. So now I'm going to display. I disconnect the input. Notice I've only disconnected the display of the input. The signal is still there because here it is. Now let me put it on the other side. Okay? So notice now what I have. Let's get 2 signals with the same magnitude of display. So one is at 2 volts, one is at 1 volt. I'm going to make them both at 1 volt. Okay? So look what happens now. The blue signal is the, whatever I called the red one. The blue signal is this pin right here. And I think we called that pin 1. Pin 2 is now the ground. We have that for both of them. Okay. And pin 3 is the red signal. So look what happens when we make pin 2 the ground. The 2 signals are equal in magnitude but opposite in phase. And that's what I want you to draw over here. I want you to draw this graph right over here. And the channel 1 volts per division is right here. You can see it. It's 0.2 volts per division. And channel 2 is also 0.2 volts per division. We did that on purpose. The time base is what per division? It's 2 milliseconds per division. And then you'll have to figure out the frequency from there. Right? The frequency is, if I go from this point, 1, 2, 2.5. So it looks like I've got 2.5 times 2 milliseconds per division. It told me that up here. All right, so you can figure out those frequencies. It hasn't changed. Here it is. From this point to this point is one cycle. Don't get confused and think you go from blue down to red down. You got to go from blue all the way through a whole period down to there. So you're looking at 1, 2, 3, 4, 5 divisions. So this is the same thing, except now you're going to draw it. And then I want you to, take a picture. I think I included in yours. Take a picture of this and attach it. Okay, get used to that because it's a good way to fill things in on a fillable PDF form. Okay, so this is the end of the experiment, but we're gonna leverage in the AC to DC part 2. We're gonna leverage the fact that a center tapped transformer gives two equal magnitudes with opposite polarity. They're out of phase. This tap might not be in the center, so then they'd be out of phase, but they would be different magnitudes. We know this is center tap because it's of equal magnitude. Okay, so I'm going to quit here, and you can fill this out between these two labs. Fill out your lab, think it through, and submit it. All right, thanks.